Right. Are we still waiting for someone? Do you think anyone is still having dinner? Should we wait a few more minutes? Thank you. Yeah, I've turned it on now. Okay, so let's talk about the problems today. So this was a contest held in Moscow about 10 years ago, and this was actually the first sub-regional I participated in. So if you turned on the common standings, you could see my name here, my name there, somewhere, and we solved 8 problems. So if you solved more than 8 problems, that you have beat me, basically. Okay. So let's get going. The first problem, A, was basically you had a list of teams, right? And you had to tell which of the teams are going to qualify to the next round using the rules that you had written here. So it's just implementation, right? There's not much going on. There are no any problems with reading the strings. It's basically just do what it says, right? Does anyone have any questions about this problem? I believe that most of the teams solve it. In the problem B, what you had basically is like a rectangle of numbers, but rectangle didn't matter. You just had a bunch of numbers. So, it had a legend about some market crash, and I believe there was like a financial crisis in Russia at that time, so it doesn't matter at all. So what the problem boils down to is that you don't worry too much about what the numbers in your set are exactly. You just care about how many times each number repeats, right? So so for each number you write down how many times it repeats. So the first number repeats A1 times, the second A2 times, and so on. And you also you can choose a single number and sell it on a particular day, and in each day the price is slightly different. So you have like another sequence of numbers So you only have like you only consider the first several days. So if there are like 10 different numbers, then you consider 10 different days. And what the problem boils down to is you can reorder the numbers in the first set so that to maximize the sum of products of the corresponding numbers, right? And this is it's quite easy to prove that if you want to maximize the sum of products, if you could rearrange both sequences, then the largest answer would occur if, for example, both sequences are sorted by increasing. It's pretty easy to prove. If something is not in order, then you can swap the numbers so that they become in order, and then you have a larger sum of products. It's easy math. So basically, since you can sort this, you can remember in which positions which numbers occur. Then you sort both sequences, and then you know where each number from the first sequence should go. So it's kind of another simple problem without any complications. Are there any concerns, questions about this problem? Yeah, and you don't even have to output the answer. So you don't even have to find the sum of products. You just sort the numbers and that's it. Okay. In the problem C was kind of interesting, at least more interesting than the first two. So what you had to do is you have a rectangle n times m. So it has n cells, and you have several buildings that you want to build there. You know heights of all buildings, but you can rearrange them in any way you want. So it's like 4, 3, and 4, and 1, and something. So what do you want to optimize is, so these are heights of these buildings, right? So what you want to optimize is the total area of walls between the buildings. So for example, we know that this has 5 feet wall, and this has 5 feet wall, and this has 3 feet wall. But since these buildings are adjacent, then here we only have a 2 feet wall, right? So we want to arrange the buildings so that the total area is minimized. And okay, so let's look at at the way we can look at this problem and calculate the total area. So let's assume that in each row and in each column the heights are first increasing or non-decreasing and then decreasing. Okay? So if this happens, then it's quite easy to calculate the total area. So if this happens in every row and every column, because here we can see that, for example, in this row it doesn't happen, but for example in this row, if you look from this side, then we see a total of we see parts of walls, but their total height is 3, right? And because 3 is the tallest one, and it doesn't matter what these numbers are here, as long as they are increasing, we are going to see 3, right? And the same from the other position. So if this condition is satisfied, then the total area that corresponds to this row is 2 times the largest height, right? And the same happens for the columns. So as long as we keep this condition, we can look at this problem in this way. So we have to minimize basically the sum of largest numbers in each row and largest numbers in each column. Okay, so hopefully we can obtain an optimal solution which doesn't have these. Okay, because if this does happen, then there are like a lot of inner walls that, and we don't want to have that. Okay, so how do we place our buildings? So we have this rectangle, and let's consider our buildings by decreasing of heights. Okay, so we start with the largest, then the second largest, and so on. And we can see that if you look at the largest building, whenever we place it, so if it has height x, then whenever we place it, it's going to contribute 2 times x, okay, because it's higher than anything. Okay, so let's just place it in the top left corner here. It won't matter too much where we're going to place it. So the next largest building, it now depends on where do we place it. If we place it here, for example, again, it will contribute twice to our answer. So we don't want that. And if we place it next to the previous building, like in the same row or in the same column, then it's going to contribute only once, right? So it's going to be plus y. We are kind of going greedy now for the start. Okay, so the next highest building, again, it can contribute either twice or once, right? So, but there are now 2 ways to place it so that it contributes once. It's either here or here, right? And it's actually better to place it here, because then we can place the 4th highest building here so that it won't contribute at all. Okay? So basically, the strategy to place our buildings is that at every point we want to keep a square here. So after that, we are going to place the next building here, and then we can place this here so that it does not contribute, and then the next here, so we get 2 free spots, and so on. So after a while, we will obtain this circle that like occupies 1 whole dimension, and then we are going to build it like this, basically. Okay. So this is how the solution goes. It's not a proof. It's like because I only use some greedy considerations. So if you want a proof, then so the proof basically boils down to, well, the first building obviously contributes twice, and then after that, you can see that out of n squared plus 1 buildings, we are going to fill up at least, let's see here. So if we have 2 buildings, we are going to occupy at least 3 spots, right? So that's like n plus 2, I think. Right? So out of largest n squared plus 1 buildings, at least n plus spots, so rows or columns, are going to be occupied. Well, because you can do better than a square and then a single number. And when we have n times n plus 1 buildings, which is this rectangle, for example, here we have 7, and an extra spot. So here we are going to have at least, I think I messed up here, it should be like this, and here we have to have at least 2n plus 2 spots. Okay, so we have a bunch of these conditions, and basically under these conditions, it is optimal to choose numbers basically in this way. Okay, so this is a kind of proof. It's like you can think of it as if you just have the numbers, you don't have these, and you only have these conditions. Then then it's natural that when you go and you meet the next condition, and you have one extra spot left from the previous phase. So you want to choose the lowest number that still fits there under this condition. Okay, so this is a kind of proof. I think it's natural that this solution work. So I don't like for a full formal explanation, but if someone wants a better explanation or someone has a question, then please ask away. Is this okay? All right. All right. The problem D. If you looked at the standings with the all teams that solved this competition, you could see that they had a lot of trouble with it. For example, our team didn't solve this problem, and some of you solved this within an hour, basically, right? So the problem was basically like a standard data structure problem. You had a data structure, and you added some numbers into it, or basically numbers with some additional information, and you had to answer queries. Basically, find the kth number and delete it, right? And out of equal numbers, you had to choose. You had to introduce the second criterion by increasing of some other field. So basically, if it were just numbers and we knew that they were all different, then it's a standard problem. We just use a trip data structure, right? And the trip can add extra numbers into the data structure and also find kth largest, right? So here we don't exactly have numbers, but rather we have to compare, we have to introduce second criterion. So to do that, instead of a trip of numbers, we will do a trip of pairs. So instead of numbers, we just compare pairs, okay? And comparison pairs is you just go pair and you write one is less than the other. So yeah, it's basically now nowadays in 2018, it's basically a standard data structure exercise, right? But back in 2008, it was 2008. It was the trip data structure was not so well known. It's only popular now the last few years, but now everyone knows it. So that's the reason why the teams at the official competition were struggling with that. Anyway, so that's pretty much all I'm going to say about this problem. Are there any questions? Ordered set. Is it it's not. I mean, I think standard set does not support operation like kth number. Oh, it's like this tree stuff, right? From the extended standard. Okay. Yeah, it's actually it's pretty good that so many of you know about this trick. I don't know about that, so I just write trips every time. But I think at least I'm good at it now that I write it a lot. Yeah, basically, if you don't know about what this is all about, basically there are some magical extra libraries in C++ that you can use, and it kind of does the same thing as trips. So if you want to know more about that, I suppose that a lot of you know, so you can just ask someone in the audience if he knows how to use it. I believe there is also tutorial in Codeforces or something. So yeah, you can look it up. It's a nice trick. if you don't like to write trip like I do. Okay, so the problem E. So what happened in the problem E? You had a certain number of problems that you have a probability to solve. So you have all these problems, and first you choose which problems are you going to solve and in which order. You know the probability that you will obtain points for this problem, and also know the time that you need to write the code. And if you don't get the point, then you still waste time. So, and there is also the time limit on the time how long the competition is going. So you want to find the problems you want to solve, and also the optimal order, so that the expected number of solved problems is as large as possible. And if there are several options, then you want to minimize the expected time. Okay. So there are a couple of observations you need to solve this efficiently, and the first observation is maybe the hardest, really, because it's concerned with the order, how you should order the problems after you have chosen which problems are you going to solve. So, okay, let's assume that we have chosen a set of problems. We don't know the order yet, and we have the probabilities here, and we have the times here, and we want to order the problems, right? So when you are concerned with an optimal order of something, one trick that you can use is basically consider any order and consider two adjacent spots here. So after that, you look at, so there are two problems that you want to place here, but you don't know the order. So you consider both options, and you see what's the criterion that one option is better than the other. Okay, so let's try and calculate. So we are minimizing the expected time, right? Because the expected number of problems is the same. It doesn't depend on the order. So let's try and minimize the time. So let's consider two options. So it's either I plus 1, or it's I plus 1 and I. So for the first, they are going to be a lot similar. So for the first here, we are going to have something until it's going to be the same as here, right? Until we arrive at the spot I, where here we are going to have pi times the sum of something plus ti, right? And after that, we are going to have pi plus 1 times something plus ti plus ti plus 1, right? And then again, something that is the same as in this case, right? And here, the difference is, here we have pi plus 1, ti plus 1, plus pi times the same thing, right? So now we are going to look at when this expression is less than this expression. So that this will mean that this order is better. Okay. All right. So let's subtract one from the other, and this order will be better if the difference is greater than 0. Less than 0. Okay. Okay, so most of this cancels out. Everything here and here and here and here cancels out. And also pi times ti cancels here, right? And these numbers cancel here. Okay, so we are left up with basically pi plus 1 times ti minus p. So here we have nothing. Here we have pi times ti plus 1. Okay? So, if we rearrange something here, I believe that so ti is positive, so we can divide by both of these numbers, and we also can carry this here. So what we are going to obtain is pi plus 1 divided by ti plus 1 is less than pi divided by ti. Okay? So what we have here is that the order of these two problems is determined by comparison of two expressions that only depend on a particular problem, right? So in the optimal order, we must have that the values of these numbers are non-increasing. Yes, non-decreasing. They're decreasing. Okay, or they can be equal. It's hard. Okay, so the reason why this is the only optimal order is that if we have a violation of that, then we must have two adjacent problems where this doesn't hold, and by this analysis we can swap these problems and obtain a better result. Okay, so the first step is that we take these quantities for every problem, and all of our given n problems are going to be sorted by non-increasing of these fractions. Okay, so this is the first step, and now we can see that, like, since this holds for any set of problems, if we are going from left to right in this order, we are considering problems in the optimal order. Okay. Well, now we get order out of the way. So if the order was fixed, it's kind of fixed now. Then this becomes our a dynamic programming, which is we are considering problems like if you consider the first I problems and we want to take basically any number of them, so out of first I, we consider all sets of problems that have total time j, not expected time, but just time. Okay, the sum of times. So total time j, and out of this we maximize the expected number of solved problems. Okay, and we have to also minimize the expected time. So what we are going to do is that the value of this dynamic programming is going to be a pair. So the first element of the pair is the largest number of solved problems, and out of all ways to obtain this number, we also store the smallest expectation of time. Okay? Because if one option is better than the other in terms of solved problems, we don't care about the time. Right? So now the solution is pretty easy, because if we consider the next problem, if we don't take it, that nothing changes, and if we do take it, then this number increases by the probability here, and also we know how much the expected time increases. And to know this difference, we have to know the time that we spent on the first several problems. So basically, if we introduce a new problem, then here we get plus pj plus I plus 1, And here we get plus pi plus 1 j plus ti plus 1. Okay, so I have all the necessary information now, and now so the solution to compute all these values, we need n times t capital time, where n is the number of problems and t is the duration of the contest. Okay, so and then out of this, in the last, like when we have considered all problems, we just take the best answer. Again, we have to compare both of these numbers to make the best, and we also have to make sure not to take too much time for solving the problem. So g has to be at most t, which is why t is here. So that's basically the solution to this problem. I think the first step is harder than the second one, to come up with this comparison technique. And one small thing here is you probably don't want to use double, because all the probabilities are given in percentages. So instead you can just multiply everything by 100 and compare integers. I don't think you should have any precision issues, because but I am not sure. Did anyone pass a solution in doubles? Probably everyone was okay with coming up with doing everything in integers. Okay, any questions about the problem? All right. The problem F was a 3D geometry problem, which everyone loves. So, what the problem was about, I suppose that like when everyone saw like the sphere and spherical triangles, everyone said, okay, I won't read this. Anyway, the problem was about a sphere so we had like a satellite, or I don't know, a rocket landing somewhere on a sphere from a certain point with a certain velocity. And we also had like 3 beacons on the surface of the planet, and it made a spherical triangle. I can draw spherical triangles. Okay, good enough. And we wanted to check if the landing occurred within this triangle. Okay. So there are a lot of 3D. There is a lot of 3D stuff you have to do here. So first, you want to determine the allocation of landing here. Okay, and there are a few ways to do that. Basically, this problem is not too much different than intersecting a line with a circle, as we did in our geometry day, right? So here you can actually reduce this problem to a 2D case, but probably a simpler way would be to have this line and to introduce a parameter t, so that after a time t we have like x plus vx times t. The coordinates are like this. So, and you want to find a point in time where the distance to the center here is exactly r, exactly the radius, because this is the moment where we reach the surface. Okay, and so if you write down the distance and you write like equals to r, or you would rather write basically, so we can suppose that this is the origin, and then the condition that the distance is r becomes that the sum of squares of these numbers is r squared. And if you work out all the brackets, you can see that this is a quadratic equation in T. So you can find the solutions, and you want to find the smallest solution among the positive ones. Yeah. So the thing is, if there could be either both solutions are positive or they are both negative, because it can be the case that we are flying away from the planet, and in this case, like we don't reach it. Okay, or we could fly off completely, and then we have no roots of the equation. Okay, so now we have the coordinates of this point, but we still want to check if it's inside the triangle. The question is, what is a triangle in a sphere? And the way to construct, the way it's constructed, is like if we have to. So out of 3 points, we consider all pairs, and then each pair of distinct points on a sphere lies on a unique great circle. Okay, so this part of the triangle is an arc of the big circle, and we consider like 3 arcs here. Okay, so now let's think about how do we check that the point is inside the triangle. Okay, let's consider the case when we are in the plane. Okay, and we have to check that a point is inside the triangle. So what happens is we have a triangle and a point. So there are a bunch of ways to check if a point is inside of a triangle, but the simplest way is basically to do as follows. So consider a side here. Okay, a side. So it has a line that passes through it, and if the point is inside the triangle, then obviously we must have that the point here and the third vertex of the triangle are on the same side, right? So obviously, if it's on the other side, then it's out of the question. The point is out of the triangle. And if we check that for all 3 sides, then what we are left with are exactly the points inside the triangle. Okay, and checking if 2 points are on the same side of a line it doesn't require too much. Basically, what we want to do is to check that the cross product of this vector and this vector, and also this vector and this vector, have the same sign. Because we want to check that this rotation and this rotation have the same direction. Okay, makes sense? So if we go back to this problem, we want to do pretty much the same thing. So let's consider 2 points on this circle here. So what the circle is the intersection of a sphere, of the sphere that we have, with a plane that passes through the origin and also these 2 points that we have. Okay. So what else do we have is we have this point and we have the third vertex of a triangle. Okay. So similarly to what we did here, we want to check that these 2 points lie to the same side of this plane. Okay. And if we do this for all pairs of points, then we have checked that the point is inside the triangle. Okay. So how do we check if 2 points are to the same side of the plane? Again, we will use cross product, but this cross product is going to be 3-dimensional. Basically, what happens is that if you have 3 vectors in 3-dimensional space, you can think about their relative position, and so either they are in the same plane, or it's good to show with fingers. Basically, it can happen like this. So if you take your fingers on the right hand, so this is the first, the second, and the third finger, right? So either they are located like this. So basically, like if you look like from the top of my thumb, then the rotation from the second to the third occurs in this direction, and on my other hand, it goes in other direction. So there are two ways of positioning of three vectors in 3D space, right? And this is usually called the right triple of vectors, and this is a left triple of vectors. So what we want to check is a triple of vectors, like if this is A, B, C, and D. So what we want to check is that the triple ABC and the triple ABD have the same type. So either they are both left or they are both right. Okay? Makes sense? That's because if D travels to the other side of the plane, then the type of the triple changes. Okay? So now we have to determine the type of a triple of vectors in three-dimensional space. And for that, we use the three-dimensional cross product of vectors. It's not a cross product. It's actually what's called a mixed product, because the cross product is defined for two vectors, and in three-dimensional space, it's another vector. But that aside, basically, if we have three vectors, like with coordinates x1, y1, z1, and three vectors, to determine the type of the triple, you write down the following determinant. Here. Okay, so this is the determinant of a 3x3 matrix, and you look at its value, and if it's 0, then the vectors are coplanar, so they lie in the same plane. If it's greater than 0, then it's right triple, and if it's less than 0, then it's left triple. Okay. If you don't want to compute the determinant, but you know how to compute the cross product, which I'm probably not going to write. Basically, it's an operation that takes two vectors and then spits out a vector that's orthogonal to both of them with a certain length. So yeah, you can take the cross product of two vectors and then take the scalar product with the third vector. That thing aside, this criterion works for determining the type of the triple, and that's basically all we need to check these. Okay, and after checking this, we have solved the problem for the spherical triangle. The last detail is that these points, the vertices of the triangle, were not given with coordinates, but rather with latitude and longitude. So the first thing you do with that is you convert this to actual rectangular coordinates. And do you want me to write down the formulas for converting? It's basically just you have two angles, and then you multiply the radius by cosines and sines and stuff. Does anyone want the formulas? I will probably mess up. So if you want to know the formulas, they're on Wikipedia, for example. Okay, it's better. At least it should be correct. So again, you see this, like what I said about the geometry. If you are good with your primitives, then you're able to solve a lot of problems. And this problem is about the primitives, but in three-dimensional geometry. We didn't discuss that, but sometimes these problems occur, so you may want to get good with that. Okay, are there still any questions or concerns here? Basically, you can worry about precision here, but in the output format, it's guaranteed that either you land outside or you land far enough from the border. So you can basically, what that means is you can ignore the epsilons, and if something is very close to 0, then it must be outside. Okay, the problem G about some multiplying stuff. Yeah, okay. So we had a bunch of points. And what happened is every second, each pair of points spawned a point in the middle of the segment between them. Okay, and these points die off. And after that, the process repeats. So that happens again and again until 2 points 2 points spawn at the same spot. And you want to determine the number of seconds until that happens. Okay, so there are like if there is 1 point, then obviously nothing happens. If there are 2 points, then a single point spawns and then dies off. If there are 3 points, like this, then what happens is we get smaller and smaller triangle. So it will nothing will ever nothing will ever spawn in the same spot, except when you have 3 points on the same line. And what happens then is, I don't know actually. The line shrinks, right? So nothing will ever happen in this case as well. Yeah, that makes sense. So this picture shrinks as well. So if we have 3 points, then nothing will ever happen. Okay, just in the case when we have 1 and 2 points. Okay, but if we have at least 4 points, then what we have here is, if you consider 4 points, let's consider like the what happens. So after first stage, we will have points here, here, and here in the middles of the sides, right, of the quadrilateral. And after this, these sides will spawn the point exactly at the very center of the original points. So the point here will have, if you write it down for this pair and this pair, what will happen is this point will have coordinates that are means of the original 4 points. Okay? So what that means is that if we have at least 4 points, then the answer is at most 2. Okay? So after, on the second step, this thing is bound to happen. So the question is the answer 1 or if it's 2? And to check if the answer is 1, we basically have to simulate the process for one step. That is, we take all points and then we take all the midpoints of all segments and check if some of the points are repeating. So if that happens, then the answer is 1. And if that doesn't happen, then we don't even bother going for the second step because we know what's going to happen. Okay? So that basically finishes the problem. Nothing happens. Nothing happens. Are there any questions here? Okay. The problem H. In the problem H, we had a bunch of flights. I believe the flights are bidirectional. Okay. So we have a bunch of bidirectional flights. So a weighted graph. And what we care about is the largest time over all pairs of cities to get from one city to another, possibly with some connections. Okay, and that time can be infinite if some cities are unreachable from each other. And what we do care about is we want to introduce an extra edge between a pair of cities, and we want to choose a we want to choose a weight here, so that to minimize this the largest distance between cities, and out of all ways to do that, we want to minimize this x. Okay. So let's solve the first part of the problem, where we have to minimize the largest time. And to do that, we want to basically what we are doing is trying all possible pairs of cities to build this extra road, and then if we want to minimize the time and we don't care about this x, then it makes sense to make x 0. Okay, so the problem is to try all pairs, place 0 here, and then find what's the largest time over all pairs. Okay, so if we just have a graph and we want to find all pairwise distances, we can use Floyd algorithm for that. It works in n³ time. Does anyone want me to talk about Floyd's algorithm? Okay, so it's very short and simple. The problem is, if we want to introduce the edge and then do Floyd every time, it will be n to the 5th. So what we do instead is we do the Floyd algorithm for the initial graph. Okay, and then so we know all distances between all points in the original graph, and if we want to find the distance between two cities in presence of this extra edge with capacity 0, with length 0, the shortest path is either the shortest path in the original graph or a path that uses this thing. So, and there are two ways to use it. Either we go here and then go from here, and we know the shortest length of these parts, or we use it the other way around. Okay, so in fact, knowing the distances in the original graph allows us to find any distance in the new graph in the presence of this edge in constant time. Okay, so what we do now to determine this the best pair and the best largest distance is we try all pairs of points, which requires n², and try all pairs of points again to choose the largest distance, and that takes n² again. And before that, we have the Floyd. Okay. So this is the first step. This is how we. This is how we do this, and to. So now we also have to determine what's the. So now, we have to determine what's the largest possible x that we can place here, so that we make the distance, we make the largest distance at least, or rather at most, our threshold that we've determined. So I believe there's a way to do that without binary search, but probably the binary search works, right? Like, okay, so the way to do this with binary search is basically, after you know the optimal largest time, you binary search for x and find the largest x where the largest distance is still the same. That's the way you do with binary search. And without the binary search, yeah, you can write inequalities. So basically, what happens? Okay, so yeah, there are some inequalities. Basically, So for each pair, we have certain conditions for this particular pair having the largest distance at most our threshold, right? So that goes something like, so if the original distance is at most threshold, then we do not care. And otherwise, we have something like the shortest of, so either the sum of these or the sum of these. So we can name it like A plus X is at most our threshold. Okay, so we do this only if the original path between this point is too long, is longer than the threshold. So we have a bunch of these, and we write down these inequalities for all pairs, and out of this we can establish what can be the largest X that satisfies all these inequalities. Okay, but still we have to do that for all pairs to that we use to construct the extra edge. Okay, and choose the best X amongst all of them. Yeah, but binary search is fine too, I think. Anyway, yeah, and you also have to check for infinities, because if you cannot make answer less than infinity with one edge, then you just output infinity and don't care. And that's the only case here. Okay, any other questions about this problem? Okay. In the problem I, you had a bunch of rectangles that did not intersect. So you had a large triangles and you have cut it in a bunch of smaller rectangles. And what you wanted to do is, so in this partition you had two rectangles already chosen, and you wanted to buy some extra rectangles here, for example, like this, so that basically if you project all the rectangles to the x-axis, then each point is covered only once, except for borders, and like borders can be at the same position. They have to be the same position. Okay, so that's what was this problem about. And most of this problem is a red herring, basically. Let's assume that we have no triangles, no rectangles here, and we just want to choose some rectangles to cover everything. Okay. So let's think about. Obviously, we have to choose a rectangle that with left side coinciding with the left side here. Okay. So its right side is over there. So after that, we want to choose a rectangle that has the left side at the same position. Okay. And then again, and then again, and then again. So we're traveling between the rectangles if they have the sides having the same x coordinate. So the way we can think about that is we start at the point 0, and having this rectangle here allows us to jump from point 0 to some x1, right? If this is x1. And now when we are at the point x1, then this triangle, this rectangle, I'm going to say triangle for the rest of the day, allows us to jump to this point x2 here. Okay? And with these jumps between the points, so a rectangle allows us to jump from exactly this point to exactly this point. And we want to use a number of jumps to make it to the right side of a large rectangle. Okay? So in fact, what we have here is a graph problem, because basically the vertices here are these coordinates, these points on the axis, and each rectangle is a directed edge, okay, from one point to another. And what we want to find here is a path from one point to another. and any path is okay. So what we do is construct this graph and run the DFS, and that's basically it. Okay. So what's the difference between this problem and the problem where we have two rectangles chosen? Is nothing, except that the rectangles have to not intersect when we project them onto the axis here, and the paths that we want to find are like a path from here to the left side of the left rectangle, and then this path in the middle, and then this path here. Okay. So, yeah, a graph problem. Who would have thought? Okay. Any questions about this? Yep. I guess you could. Yeah, it's like you can do dynamic programming with like, can you reach a particular point and then try all rectangles and something like that. Basically, it would be the same really, because we have here, what we have here is a directed acyclic graph, and you want to find a path in it, and there are a whole lot of ways to do that. So yeah, you could go with dynamic programming as well. All right, any questions? So the problem J was long at the very least, and so how many people here have read the problem? Okay. Yeah, not too much. So in a nutshell, what you had is an expression that was made out of matches, and it was some additions, subtractions, and also Roman numbers. So everything we know and love. And what we could do is take matches out of the picture and move them to other locations, so that the new picture is a correct arithmetical statement. And you have to output all ways to do that. Okay, so where do we start here? Okay. So first of all, what we would like to be able to do is, if we have an expression, we want to check if it's actually a correct arithmetical expression. Okay? There are a bunch of ways to do that. Basically, since here our expressions are not too complex, because we don't have brackets, we don't have a priority of operations, basically what we can do is to find the equality sign. It's going to be at a single position, and then like find all the operations to the both sides, and then parse the Roman numbers. So and we also have to check that they are actually correct Roman numbers, and then we evaluate both parts. And we have to check that like no two signs are in neighboring spots, and the stuff we usually have in arithmetic expression. So the hardest part here is probably how to. It's not too hard, but you have to evaluate Roman numbers. If you are given a string, but you have rules here, so you can just write a function that takes a string and basically implements these rules and returns the value. Okay, doesn't seem too hard. But now we come to moving the matches, and basically what you have to do is to try always to take a match and move it somewhere else, right? And the other thing that you have to consider is that you can kind of take a match and then place it in a spot between two characters. Okay. So if you want to account for all the ways that you can do that, a convenient thing to do is, if you have a string of characters like this, And so now you want to be able to go into the spots here. So okay, let's introduce a new character that is the spot and kind of space our string out here. Okay, so these spots, you should ignore them for all other purposes than moving the matches. So basically, if you parse a number and there are spaces, then you just ignore them. Okay, but it's convenient to have them because now we basically just try all spots, try all pairs of spots, and then try to move a match from here to here in any possible way. Okay, and there are actually not a lot of ways to do that. Like you have a table here, so you can just implement all of these ways basically. So these ways are based on which character is here and which character is here. So we have to consider all transformations that depend on this pair of characters. And like there are several ways that you can approach a code like this. So you can write a lot of conditions that depend on these pairs, but a more convenient way would be to use some like data structures that you prefill with all the ways. So basically, what you want to have is a map from a pair of characters to a sequence of pairs of characters, and these are going to be our transformations. And so if you prefill this map with all possible transformations, then in the actual code you don't have to think about what these transformations are, right? Because you take this pair of characters, you look up in the table what are all the possible transformations, and then you just try all of them. Okay, so that is the way you can kind of mitigate the complexity in the number of options that you have here. Because the only way where you care about what the transformations are is when you fill this table. Okay. Yes, and you also have transformations where you take a match and then place it back into the same position. But you can probably just you can do the same thing basically. So for each character, you can make a list of what options do you have for doing something within the character. So while this problem may seem not too nice, it actually, like the solution consists of a lot of parts, right? So first you have parsing the string, then you have parsing the numbers, then you have moving the matches in all possible ways. But if you look at each of these parts individually, it's not too hard. So you have to parse the numbers. To parse a number, okay, that's a small function. You have to parse an expression. Okay, that's another small function. And well, moving the matches is like another part of the code. So it's always a good idea to look at the problem and say, okay, the solution consists of several parts, and all of them are not too hard. So I'm going to approach all of these parts and implement them, and then I will make the correct solution out of it. Other than trying to go head first in writing the solution, and not thinking about the details, and not thinking about how to distribute different parts of the problems, and then having a lot of trouble basically. Another thing, if you distribute the solution into several parts, it will be much easier to look for mistakes in your solution, because you can debug each part individually. Okay. So yeah, that's a technical problem for you. Any other questions about the problem? All right. the problem K. So in the problem K, we had a sequence of numbers, which consisted, like, we could think of it as a set of segments with same numbers, and in one operation we could take a segment of equal numbers and change them all into a different number. Okay, and we had to make all the sequence consist of equal numbers in the smallest amount of operations. Okay. So the way we can think about this is that instead of okay, let's suppose that we have a segment of equal numbers that we are going to change, right? So the first thing is, like, we have to choose maximal segments at each stage, because it doesn't make sense to lose some extra numbers here that are the same. Okay, so segments are kind of indivisible for our purposes. The other thing is that if you have a sequence, if you have a segment and we want to change it into something, then it only makes sense to do it so that the segment merges with something else, because otherwise we didn't actually achieve anything by changing this segment. Or if we could, if we are going to achieve something so that it merges with something else, then we might as well wait for that other thing to happen and then merge it with it. Okay, so the moral is the segment only changes to one of the neighboring numbers. Okay, so let's look at I was forgetting about the thing that I was going to get to. The thing is, if we are going to merge a segment with something else, so if it changes into twos, then since this segment is basically since these numbers are basically together forever, then we might as well just delete them. Okay, it's just another way of thinking about it, and the solution is going to be easier to describe in this way. So we can think about the problem as choose a segment of equal numbers and delete them. Okay, this is almost an equivalent problem, except that the answer is like one greater than to the original problem. Okay, so before the last step, when we delete the last segment, everything is the same numbers. So that's the answer that we want. Okay, so the new problem now is that we can take a segment of equal numbers and delete them all, and we want to find the shortest number of moves to delete everything. Okay. Okay. So let's think about how can we do that. Let's consider our sequence and look at the first number. Okay. So what can happen to the first number? There are a couple of things. The first thing is that, well, eventually it will get deleted. So either we delete it as a segment of length 1 at some point, in which case the answer is going to be 1 plus the answer for everything else. Okay. The other thing that could happen is that we still delete it, but we delete it as a part of a larger segment. Okay. So if that's going to happen, let's see what is the. So there's going to be the segment which is now can be still spread out, right? So it becomes a segment later. So it could be that we delete these numbers in one segment, but before that we have to erase everything here and here, and then we can go for these three numbers together. Okay. So let's look what is the next number in our segment that we are going to use. Okay, in the operation that deletes this character. Okay, so before we do that, we have to erase everything here between these two numbers, between these two ones, correct? And so everything in here has to be erased independently of everything else. Okay, so in our answer we have to add up the answer for this subsegment. Okay, so if we are able to solve a problem for a subsegment, then we just take the answer for this one. Okay, and we may assume that we do this basically at the start. Okay, so now that we have done this, there is nothing here. These ones are together finally, and we may as well treat it as a single number because they are indivisible now. So if this is a single number, then what we are left with is exactly this segment. Okay, so so to obtain the answer, we have to find the answers for some smaller segments of the original sequence. And to do that, we do the subsegment dynamic programming, which is basically we want to find the answer for every subsegment here. And the transitions is either we cut off the first character and add 1 to the answer for this suffix, or we look at the first character and then look at all occurrences of the same character and then try to improve our answer with the sum of this segment, the answer for this segment, and the answer for this segment. Okay? And that's basically it. That's the whole solution. Are there any questions about why is this correct? Or like some of the reasoning I was using? Okay, so our solution has n squared states because, well, roughly n squared states because that's the number of states. And to compute every particular answer, we have to go over all occurrences of the same number here. And that multiplies the complexity by another n. So the solution works in n cubed. Okay. Well, that's the whole solution. There are all other kinds of dynamic programming that you could come up with, and most of them probably have to, most of them they are probably too slow. But the thing is, it's a standard trick to, well, in these problems where you do like where you erase segments or do something with segments in a sequence, the tricks are first you want to look what happens to the first number in the segment, and that usually allows you to obtain a faster solution than if you try to go for like consider more options. And another trick is to think what is the last operation that occurs, and we can prove that in a sequence, in an optimal sequence for every segment, we can make the operation that involves this number the last operation. So, well, this is not probably not very good illustration of this because we didn't exactly use it, but well, anyway, this is just the word of advice. Okay, are there any questions about the solution? Yeah. Okay, so apparently another solution is to consider operations in the reverse order with like some details. Probably if you want to, you may try to work out the details for yourself. Okay, the last problem, L, was about the largest streak of unlucky numbers between, like, out of all numbers that consisted of 2n digits. Okay, and a number is lucky if, so we have 2n digits. If the sum here is equal to the sum here, then the number is lucky, and otherwise it's unlucky. Okay, so I want to find the largest run of unlucky numbers, and it takes just a few observations to solve this problem. The first observation is, like, if we have n digits here, then the number x times 10 to the nth plus 1 is always lucky, because this is exactly the number when we have x here and x here, where x is some number in the range, so it doesn't exceed 10 to the nth. Okay, so that means that out of all numbers from 0 to 10 to the 2n minus 1, we have this equally spaced lucky numbers at distance 10 to the n and 10 to the n plus 1. Okay, so that means that our streak certainly cannot have more than 10 to the n element, 10 to the nth elements, and even I think so. The largest gap here is at most 10 to the n minus 1. I think so. Okay, so the answer certainly cannot get larger than that. And if we find the streak that has exactly this many elements, then basically we are done, because we've proved that we cannot go larger. And finding the streak is easy because you can just take the streak between the 0 and the next lucky number. So it's the streak between the numbers all zeros and then 1, and the number 1 and all zeros. Okay, so you can see that no numbers in this range can be lucky, because if we have 0 here and some non-zero here, then we cannot match sums, and this number is okay, right? So that's one possible answer. Probably there are others, but anyway, not to say about this problem. Yeah, in the sample you have a red herring, the number that looks complicated, but you don't have to look for that. Okay. Okay. So instead of this, yeah, I missed that. So instead of this, you will go for the last run here. So the last run consists of like 9, 9, 9. Here is 8, and the 9th here, and here it starts with all 9s, and here we have all 9s and an 8. And you can check that it still works, basically, for the same reasons. Okay. So, with that out of the way, that were today's problems, and I think everyone did very good job on the problems. Okay, so now I'm going to hang around. If you want to ask me questions, you can. And other than that, I hope you had a great time so far. Tomorrow you will have like a free day or a sponsored day. I don't know if it's actually free. But yeah, on Friday we will return to doing contests. So that's it for now. Thank you. The next topic, I'll surprise you.